Hello everyone and welcome back. We're now in 8.3. We're talking about a confidence interval for the mean. Now back in chapter 7 we talked about the mean twice. First when we had the population standard deviation, then we could use a z-test, and again when we only had the sample standard deviation, in which case we had to do a t-test. In chapter 8 we're skipping straight to the better assumption that we do not have the population standard deviation. So we still have a standard deviation, but it's the sample standard deviation. So again, we're going to be talking about a t-test. We're going to be using t as our critical value. So we're going to start just by looking at an example of how we would state the confidence interval for a mean. So looking at that first question, we're looking at the random variable and the parameter. Of course, x is the random variable, and mu, remember mu is it's the true mean of the random variable in the population. The assumptions, we're not making any distinction here about z and t. We're going straight to the case where we only know the sample standard deviation. So there's only two assumptions here if you compare that back to chapter 7 where we had 3. So the first, exactly what you'd expect, a random sample of size n is taken. And the second, one of two cases, or maybe even 3, the population is known to be normally distributed. So we might be told that it's normally distributed, or we might actually have to do some of the tests we learned to show that it's normally distributed. Or that's not the only way that we know that, or we have something that's normally distributed. The sample size can be over 30. So that's probably exactly what you were expecting. Now the confidence interval here is also probably exactly what you were expecting. That is, it's the point estimator, in this case x bar, and minus the margin of error, that's the capital E. That contains the population mean, mu, and then the upper bound is x bar, that is the point estimate from the sample, plus the margin of error. The margin of error here, notice, has a t in it. That's t sub c. That's the bridge between the level of confidence and the confidence interval, because of course E makes the width of that confidence interval. There's an S there, and notice that that S is the sample standard deviation. And S is being divided by the square root of the sample size n. So E, our margin of error, is that determines the width of the confidence interval because it's what we're adding and subtracting to the point estimate, in this case for means, x bar, to trap, that is to contain, the true population proportion, mu. Now, x bar is, of course, the point estimator for the population parameter, the population mean, mu. S is, and this is important, this is why we're using t, S is the sample standard deviation. Remember sigma, the Greek letter sigma, is the population standard deviation. So when you see S, you've got the sample standard deviation. N is our sample size, so no great surprise there. And E is called the margin of error. That's the thing that we're adding and subtracting to x bar to get that interval that contains the true population mean, C% of the time. Now, T sub C is our critical value. T sub C is a t-score, and it's a t-score because we do not know the population standard deviation. It's the critical value, and remember that it's the critical value where we get C from taking the complement of alpha. So that's also a bridge between a hypothesis test and a confidence interval. C, our confidence level, is the complement of alpha. So the statistical interpretation, so we say something along the lines that there is a C% chance that the interval, we show it exactly the way we did before, that point statistic x bar, and it is being added and subtracted to with E. So we're subtracting E to get the left endpoint, and we're adding e to get the right endpoint, and that is containing or capturing or is the endpoints for an interval that contains that population mean mu. Now the real-world interpretation is when we say this as close to a useful way as possible. We remember our units. So we say, what that interval is and what the units are for it. In your homework, you're going to find some questions that ask you for the critical value t sub c. So we're going to go through that as a separate question, but remember, the goal here really is to find a confidence interval for a population mean when the population standard deviation is not known. But we're going to start just by finding some critical values, t sub c's. So in the past, even when I was taking this course as a student, we had tables for this, and we actually found the number closest to the area, the probability that we were interested in, and then we figured out what values of t were closest to that. I'm going to talk you through using Bell. If you'd rather, you can always use the methods that Kate talks about in the book, where she uses the built-in functions of the calculator. And when we do that, we're going to use the inside area. So I'm going to first talk you through finding the critical value t sub c when c is 90% for a random sample of 350. So right now, I'm talking you through how to do this in your calculator. So go to Program, go to Bell, then make sure it appears on your screen and press Enter again to run it. That first question says, do you want to calculate the probability or do you want to find the boundary? Well, we've got that the probability c is 90%, so we want the boundary. So that's a 1 for that question. The next question says, is this normal or t? Well, we're interested in finding the critical value for a mean when we do not know sigma. So therefore it's a t, so that next question you're going to put a 1 in for t. It's going to ask you for the degree of freedom, and remember the degree of freedom is n minus 1, so enter 349, that is 1 less than 350, for the degrees of freedom, press Enter. Now, it's going to ask us, do you want x's? Well, that would be if we were looking for the confidence interval itself, but we're interested here just in the critical value, so instead of asking for an x value, we're going to ask for a t value, so a 1 for that. It's going to ask us for the probability. Now in your homework it'll have extraordinary numbers that are randomly created by the computer. But here we're just looking at 90%, so I'm going to enter 0.9. And then I'm interested in that interval that captures 90% of the data. So that's the inside area, and the inside area is 2. And then there's a fair amount of computation. It's interesting to see a calculator working that hard. And you've got the left and the right endpoint of that interval. We're interested in just the critical value, so we're not interested in that plus or minus business. So just the positive, the right endpoint. 1.64923135 is what it shows on my calculator. Looks like we're rounding this to 3 decimal places. So after that third decimal place, the 9, I see a 2. So we round down. We say t sub 0.9, that's t sub c, equals 1.649. And it's good to remind yourself of the degrees of freedom. There's 349 degrees of freedom here. Now, we can do this with Bell as well. We can actually find a confidence interval. And we're going to step through doing that. But I will point out that this is a built-in function in your calculator. So we're going to use Bell one more time just to show how that generalizes. And then we'll use the t interval function in your calculator. So what your calculator is going to ask for is the sample mean. So you have to know that, and you have to know at least the sample standard deviation. And we're making that assumption that we know the sample standard deviation. So for Bell to work when we're finding an interval, we're going to be asked for the sample mean. We're also going to be asked for the standard deviation. Now, to do that, we're going to actually have to do some arithmetic. So that's s divided by the square root of n. We're going to enter that into the calculator when the time comes. And again, the degree of freedom is 1 minus n. And again, we're going to be interested in the inside area. So we're going to use Bell to find a confidence interval when we have a confidence level of 95% for a random sample of 29, so n equals 29. Now that's not enough to assume that the random variable is normally distributed. We're told that our sample mean, x bar, is 56, and our sample standard deviation, so we're using the calculator's notation here, capital S sub x. A lowercase s would work just as well for the sample standard deviation from a normally distributed population. So the fact that the sample size is 29 and that's less than 30 doesn't bother us here. Okay, so again, I'm going to step you through using Bell to do this. So press Program on your calculator, the PRGM button, select Bell, press Enter again to run Bell. Again, you've got the area, that is your confidence level of 95%. So in that first question, when it says, do you want to calculate the probability or do you already know the probability and want the boundary, you're going to enter a 1 because we want to know the boundary. That boundary is actually going to be the confidence interval. The second question, is this normal or t? Well, we do not know the population standard deviation. So we're going to say this is a t distribution. The degree of freedom is 28. That's 29 minus 1. So that's the next question that comes up. And then now, instead of saying we're just interested in that t sub c, we're now interested in finding the x. So that is the actual value in whatever units this question came to us in x values. So we're going to enter a 0 there. So then it says, well, okay, that's fine. You've got to tell us the mean. The mean is 56, so I'm entering a 56. And the standard deviation is not 8.6. We're letting the standard deviation, the sample standard deviation, stand in for the population standard deviation. That's why we're doing a t-test. But that means that we have to take the standard deviation and divide it by the square root of n. This isn't the square root of the degrees of freedom. It's not the square root of 28. It's the square root of 29 down there in the denominator. And press Enter again. Now it asks us for the probability. That's our confidence level, 0.95. And then it says left-tailed, right-tailed, inside or outside. We want the inside area because we want to capture 95% of that probability. Press Enter again. And we've got a left and a right endpoint to our interval. It looks like when we round to 2 decimal places, 52.73, and the upper limit, 59.27. And remind, of course, yourself of the confidence level. So it would say that there's a 95% chance that the true population mean is in the interval between 52.73 and 59.27. But there's an even easier way, and that is t-interval. So we're going to do exactly the same problem again, but we're going to use the t-interval function on our calculator. One of the biggest reasons that t-interval is easier is that we don't have to use that formula for the standard deviation that says take the standard deviation, whether it's the population of the sample, and divide it by the square root of n. And the emphasis in that sentence is that we do not need to do that. So to find t-interval, press Stat, go over to Tests. It's not on the first screen that I see, but I see a z-interval, so I'm going to go down, and right below the z-interval I see a t-interval. So that on my calculator is the 8th option down in Tests in the Stat menu. So I'm going to press Enter. Make sure that Stats instead of Data is selected. If Data is selected, it's going to ask you for a list. So go over to the word Stats if it isn't selected already, and press Enter above the word Stats. And then it's going to ask you for the statistics. And of course, all of this is from the sample, so some sample statistics here. So the sample mean is 56, so enter it. The standard deviation, and that's the sample standard deviation, S sub x, is 8.6. So enter it. You do not have to divide by the square root of n when you use t-interval. And the reminder there is it's asking you for S sub x. It's asking you for the sample standard deviation. That's n, not the degrees of freedom, so make sure that for n you enter 29. The confidence level, the C level, is 0.95. And then go down over calculate, press enter. You see quite a bit of work is happening by a calculator standards. And we get that exact same interval, maybe a little bit easier, and that's always a good thing. So that interval with a 95% level of confidence contains the true population mean. Okay, so let's look at an example, and we return to 20 IQ scores of famous people. So here's a table containing 20 IQ scores of famous people. And just like in your homework, when the computer generates a table of data, in this case, I think Kate really did collect this data from the source that she mentioned back in chapter 7. And I think it's the same data. This is going to be entered into our calculator as a list. So if you want to pause right now and find a list and load this data into it, that would be a good place to start. Okay, so if you've got this data loaded into your calculator, we can continue looking through this. So there's 20 data points for the IQs of 20 randomly selected famous people. It says a random sample of 20 IQ scores of famous people was taken, information from the website of IQ of famous people, and then using a random number generator, so I'm thinking this was a simple random sample, to pick 20 of them. Find a 98% confidence interval for the IQ of a famous person. So you've got that data loaded into one of the lists, and so the first thing we do is we say what the random variable here is. So x is the IQ of a famous person. We're interested in the population mean, that is the average IQ of all famous people. So we want to use a sample to make a claim about the population. So we've got 20 of these x's, of these random variables. That's our sample. And we're going to use that relatively small amount of information, assume it really was randomly selected to do this. So one of the first things we have to remind ourselves is this was a simple random sample. She used a random number generator to choose 20 of these famous people at random, and she put it in a table, and that's what we just entered into our calculator. Now, we do need to talk about the standard deviation, and if you reread the question, it never says anything about the standard deviation. So you might say, well, maybe we need to run one of those 3 tests we've got to show that the data is normally distributed. Or maybe we should simply say we don't know that the data is normally distributed, and maybe the test is unreliable. But just like height and blood pressure and cholesterol level, the IQ scores are normally distributed. So we can say that that is one of the sets of data that we know are normally distributed. So now we go into our calculator. So the first thing, of course, that you may have already done is gone into the statistics menu, then edited a list. I'm saying L1 here because that's where I put it. But if you've already got something in L1, put it somewhere else. You'll be given that choice when you get into the menu. So we're going to go into T interval just because it's so much easier. It does all that business with the standard deviation for us. So again, that's the stat menu. And then calculate, and then T interval, which of course should be tests, and then down to T interval. So stat to tests to T interval. So that calculate should be tests. So on my calculator, T interval is down there at number 8. And then we put in the data. We say that, so now make sure that data is selected. That next question is the list that you put the data in. I put it in L1. The frequency 1 and the standard deviate, or the confidence level here is 0.98. So got your list in there. You've got your frequency defaulting hopefully to 1, or you can change it to 1 if you need to. Go down to calculate and Your calculator works away and it computes that interval. So I'm seeing 128.78, which looks like I rounded to 0.8, and 162.02, which it looks like I rounded to 0.0. And then we remind ourselves that that's a 98% confidence level. Now, we know the units here. We know what this is talking about. We can say this nicely. The average IQ of famous people is between 128.8 and 162.0, which is a nice end to our first example looking at a confidence interval for population means. Okay, our last example of a confidence interval for population means. So example 10, the data in table 8.3.3, you can find it in your book, are the life expectancies for men in European countries in 2011. And that's where the data came from, the World Health Organization. Find the 99% confidence interval for the mean life expectancy of men in Europe. And I've got the calculator images down there to help you out. That's a lot of data. So you can definitely load this into your calculator. Make sure you get the same results that I get. Or you can notice that I have given you the screenshots of what this looks like on your calculator. So if you go into T interval and go over to data, you can use that, whatever list that is, in this case L1. Here the confidence level is 99%, and then you can get that T interval. It's giving you a bunch of other data too about the sample. It's telling you what the sample mean is, 73.73584906, and the sample standard deviation 5.728306715, and that sample size was 53. So let's go through and use this data to state our confidence interval. So the first thing is our random variable. So X is the life expectancy of a European male, and mu is the population parameter. So in this case, the mean life expectancy of all European men. So the first thing we need to check is that this is in fact a simple random sample. It's pretty close to the number of European countries, so I'm going to guess that it's all of the countries that they have data for in Europe. So I'm going to say that the requirement for a simple random sample is satisfied because perhaps this is a census. That is, perhaps it covers everyone. And then we notice that that's a lot of data points. N equals 53, which is bigger than 30. So we can say, just because of that being bigger than 30, that the random variable is normally distributed. Using our calculator, we can say in the statistical interpretation that interval 71.6 to 75.8 contains the true population mean, the average life expectancy of men in Europe with a 99% confidence. But this is an excellent example and a great place to end Chapter 8 because we can say this really clearly, like something you'd read in a magazine or a newspaper. We can say that the average, that's the way that you'd say mean to most folks, lifespan or life expectancy of European men is between, we've got units here, 71.6 and 75.8 years. And make sure you get that years in there as well. Okay, everyone, thanks. That wraps up Chapter 8. We'll be looking forward to some quizzes and an exam on that. If you've got questions, you can post them to the forums. You can send me an email. If you need to find a reason to be in touch just to send an email and talk to someone, I'm more than happy to do that. Okay, have a great one. Bye.